Lucia Moura. So Lucia is currently the professor of mathematics in the School of Electrical and Computer Science at the University of Ottawa. So this morning she'll be speaking to us about covering arrays. So without further ado, let's welcome Lucia.
Hi, thank you very much. So let's get set up. Okay, so today, thank you very much for organizing this amazing conference, and I decided to talk about the one theme that is both I and Charlie Coburn are passionate about, which are covering arrays. Before, if you read my abstract, I did a little research to see how many of Charlie's articles involve in the title covering arrays, or locating arrays, detecting arrays, which are special or generalized forms of it. And I found 20% of them, 20% of his publications, both conferences and journals, 20% of Charlie's publications are in covering arrays. So I'm gonna give a general introduction. I'm not talking about the coolest, newest result, but just to give you a flavor about the various aspects of this research in covering arrays in the 20 and so minutes I have. I'm glad Charlie is there. You know, this parallel session setup is a little bit complicated. You go to your birthday party and there are 2 rooms, right? So I'm honored you're here. And I'm also glad that several of the definitions and setup already were covered in Charlie's talk, so I might make it to presenting this in my training. So this is where a lot of the research started popping up in a more organized form. I think in late 90s. I think the first time the name covering arrays appeared in an article was by this article by Lewis Sloan, 96. Although the object had been studied in many forms even before that. Around at the same time, these people in Bell Labs at the time created this AETG software, which, you know, at the beginning they were doing greedy algorithms for interaction testing, but, you know, we soon realized what they are doing. They're selling covering arrays for $20,000 a license, I think. And at the same time, there were some theses that in the area, my friend Brett Stevens was doing his thesis on transversal packings and covers, which are nothing more than covering and packing arrays. That's my first co-author paper was with Brett on lower bounds for those transversal covers, which are covering arrays. Also, Chatinev concentrated on the covering arrays for string 3. Brett's thesis was more in string 2 and Mark Chatinev. By 2004, we already had an amazing survey article, which is still, I think, the main starting point for work in the area, where there is already a lot of collection of results in this area. So that's the survey article by Charlie in 2004. So it all comes, you know, from the design theory point of view. We are looking at a generalization of orthogonal arrays. I'm presenting here the definition of an orthogonal array with index 1. So let's just do index 1. And covering arrays generalized naturally. We have an array with k columns, symbols, p symbols, and a certain strength of interaction, t. In this case of this example, t is equal to 3. And this means that for an orthogonal array, every 3-way interaction, or if you set up any 3 columns and any 3 couple of symbols on those columns, it appears in exactly 1 row. So with the TV and K specified, the orthogonal array size, number of rows is set to be in V to the T exactly. But there is a limitation because I don't have orthogonal arrays for any K. Indeed, for this case, I wouldn't be able to have, let's say, more than V plus 1 columns for T equals to 2, or V plus 2 columns for T equals to 3, for instance. So if I want to cover interactions, then we will generalize this for covering arrays. So now I have many more columns that I would like this T-way interactions covered by some row. So I still have T, V, and K. N is the number of rows of the array, which I don't know, but I would like to minimize. And the property is that if I pick any T columns and I look over the rows, I will find every T tuple of the alphabet appear in some row. So there is, you can see the 0, 0, 1 up to the 1, 1, 1 appear in some row. There are some repeats. So these are the main parameters, T, K, and V. V symbols, K columns. T is the strength of the interaction, in this case is 3. And I'd like the minimum number of rows achieving that two-way coverage. So this is the famous, I don't know which paper I took this one, I don't have the reference, but certainly some of Charlie's papers probably showing here an example of a system with 4 factors or parameters, each one having 3 possible values for a system I want to test. This is interaction between web browser, operating system, type of network connection, and printer use. And if I believe that a fault may be caused by interaction of 2 of the factors, then I would like to have a covering array of strings 2 to make sure that as I run my tests, in this case I have 9 tests, every pairwise interaction of factors is covered somewhere. So if I have, I guess, the typical Brett example, Windows with Internet Explorer, for sure, that row here, number 4, is going to cause a failure. Even though this is not a locating array, I have a likely culprit about who could be the interaction that's causing that. But indeed, it's not a locating array, as Charlie has defined it. So if this is the only failing row, because this is indeed a orthogonal array, every pairwise interaction appears exactly once. So I don't know if this pairwise interaction is a problem, or that, or that, or that. But I do detect, and I can be sure that my test set will capture any test that contain a pairwise interaction. So that's the applications. And as we generalize from orthogonal arrays, you have this beautiful mathematical problem with uniform alphabet for every column, etc. In real world, that's not the case. So there are specific, some interesting generalizations of covering arrays that people have looked at. The first important one is mixed alphabets. Not every parameter has the same number of possible values. In that case, it was 3. So I could have different alphabets per column. The definition of the covering array remains the same. There's no problem because I'm not insisting on exact coverage, but minimal coverage, so it works. Forbidden interaction is a very difficult problem to solve in general, but that's, again, one of the most important for applications because, as Charlie mentioned in the talk today, some combination of values might cause an explosion in the lab for the chemical experiments. In some cases, they might be simply not available. So if I am planning to use an array like this, but there isn't a test that can run, let's say, Explorer with a Mac, then, my first reaction, I would remove this row, but as I remove this row, I am uncovering other interactions that I must test, like the IE with the LAN, the map with the network, etc. So it's not as simple. And in some versions of it, the problem has been shown to be incomplete. Another interesting generalization is variable strength. I'm going to talk a little bit about that, but you don't need to cover every pairwise interaction. Some factors that you might want to cover more fully, and some others do not cover. Some parameters do not interact, so I do not care about them being covered. So this is not about prohibiting interactions, but not caring about some of them. And I could, by taking advantage of that, minimize even further the number of tests. In error location, which is this extension to locating arrays, detecting arrays, and others that exist. So here is an example of the mixed alphabet. So it's just so you see one example of a covering array in which the number of values here, I have a binary, ternary, and again, you know, all the definitions go through. I want to make sure that every, in this case, pairwise interaction appears somewhere. So there is no problem about having different alphabets. Of course, there is the problem about finding good arrays with mixed alphabets. That's not so easy. So here is an example for variable, to motivate a bit the variable strength. It has been proposed by some people, I think Christine Cheng, for instance, proposed the idea of using variable strength in the following scenario. You have a system in which you have outputs. Those outputs depend on some inputs, some sets of inputs. So, for instance, this output X depends on input A and B only. So A and B interact together to influence an output. For Y, I would have B, C, and D. And for Z, I have those. There is no output that is influenced by, let's say, A and E together. So that's an interaction I do not care. So a variable strength covering array is nothing more than putting a hypergraph where the vertices of this hypergraph are the columns of the array. And I put edges or hyper edges on the factors that interact together to influence the outcome of the system. And then here is an example of a covering array on this hypergraph. If you look at columns A and B, you see every binary tuple appearing once. If I look at B, C, D, I see every ternary tuple appearing at least once, exactly once in this case, because I have a tests. But I don't care about B and E, and then the C, B, and E are identical columns, and those interactions are not important. So that's a motivation for variable strength. Okay, so here I'm going to go over some of the, okay, so I have this watch of my grad students. I'm seeing how many steps she did yesterday. Okay. Okay. So this is the important, you know, for the standard covering array where all the parameters are well behaved, only one alphabet, etc. I could substitute it by k different alphabets, no problem. I would like to have the minimum n for which a covering arrays with t, k, and v fixed exist. So it's minimizing the number of rows, and the other parameters are there. The trivial lower bound is b to the t, because I have to cover at least b to the t interactions. If it's exactly b to the t, I'm dealing with an orthogonal array, and this lower bound is met if and only if an orthogonal array exists. Also, if an orthogonal array does not exist, I know the covering array number has to be at least b to the t plus 1. Here is my first co-author paper in my life with Brett Stevens during his PhD thesis. We derived some other lower bounds. I'm not going to talk too much about it, but there isn't a lot of results in lower bounds. I haven't seen much after that. You know, it's very difficult to establish lower bounds, but upper bounds in construction are easier. And there are plenty of those. In terms of asymptotic behavior, it's completely understood for the case of t equals to 2 that as I keep k and t, t2 and b alphabet fixed. As k grows, the covering array number behaves asymptotically as b over 2 log k. This is a couple of papers by Gargano Corner and Vaccaro that established it. For the case of higher t, I have also an upper bound that for t fixed this polynomial on v in log k. Sorry, here also the v and t fixed. Okay. There are better bounds than this. This I'm giving one of these. I think there is better bounds from other probabilistic methods. So in general, as v and t are fixed, cover array number grows as log k, which is good news. As the number of parameters grow, the number of rows is really log k. So this makes it very practical. I'd like to mention some important things that happen in this area. If you want to build one of those one important occurrence was the density-based greedy algorithm that Charlie and other co-authors developed at some point. We had the AETG software that was a greedy method that each time tried to cover the most uncovert interactions. But if you actually solve that, each of these iterations, I have only logged k iterations proven, but each iteration is solving an NP-complete problem. So instead they approximate. So those methods either have to sacrifice polynomial time or logarithm guarantee. While these two articles were the first time in which we have a polynomial time algorithm which insisted instead of covering the most interactions uncovered so far at each step, at each new test, it covered at least an average number of uncovered interactions. And that we could achieve polynomial time and logarithm guarantee at the same time. This was the first paper for t equals 2, and this is when this is generalized for general t. The same idea works well when you look at variable strengths. You just start with less interactions to be covered. But the same results work, and the logarithm is in the number of edges of that hypergraph that define the covering rate. So here is some experiments. I think I'm going to skip this, but it shows how I could have a variable strength in which my hypergraph is a Steiner triple system on the columns. So it is not a strength 2, these are the best known, and it's not a strength 3. I'm requiring less interactions, and I get the number of rows in between. I'm going to go on because it is not important to say. So here, this survey of Charlie details several of the known constructions. For the case of t equals to 2 and binary alphabet problems completely solved, very elegant construction that comes from the extremal set theory and can be shown to be optimal using Erdős-Korávin theorems. You just take columns that are incidence vectors of, for a fixed number of rows, we maximize the column, and you sort of use that to determine the covering array number. So if I have a certain number of columns, the maximum number of rows, the maximum number of columns is given by incidence vectors of sets that are n over 2 in size, while the first row is all zeros, let's say. So this gives the maximum number of columns, and as I pick the best n for which this number of columns is at least the number of columns that I need, I determine the covering array number for 2. For all the cases we don't have, and then we have different constructions, we don't have an optimal, general optimal solution. There are direct constructions, algebraic, some that are going to be discussed today, recursive constructions, and if you don't know what is known, you go to Charlie's covering array tables that summarize what's the best known covering arrays for T's from 2 to 6 and B from 2 to 25. So each of these combination TV gives a page like this where the current records for different values are given. And all you need here is these two values, K, number of rows, and N. This tells us there is a covering array of 64 rows for number of columns 6. So if your number of columns is 7, what's the best you can do? Well, get 8, drop one column, and you can get it with 88 rows. So it is, this problem is really fix N, maximize K, or fix K, minimize N. Normally we look at fix K, minimize N, and you can go to the next K to obtain the best N possible for the number of parameters K that you have. Okay, so here, a sample. At the beginning, you know, a lot is direct constructions. As you go on in the table, what are the winning constructions are recursive combinations of smaller ingredients. This is the existence of an orthogonal array. These are probably simulated annealing. This is a construction by finite fields that sort of generalizes this, and so on. So, and then this is what real constructions are given, how this approximates, you know, in this log scale, the logarithmic growth of covering arrays when T and B are fixed. Okay, so mixed alphabets exists. This is one of the first articles that talk about the so-called small cases K equal 4 and generalized sum. The basic product construction that works for general covering arrays also works for the alphabets as well as with respect to sizes of the alphabets. And this is a real interesting paper by Charlie in which this construction is taken to another level, in which he explores the don't cares that occur naturally for this mixed alphabet cases to be able to really, really minimize the size of the covering array. I will not tell you about the construction, but here you can see the don't care. So this is a mixed alphabet covering array in which the two first are 5, alphabet 5, then I have 6, alphabet 3, and then I have 13 binary alphabets. All the coverage is given by the numbers, and the starter don't care that you can fill arbitrarily with any other value of the alphabet. And then if you have a lot of this don't care, you can actually, as you do a cut and paste product construction, you can actually shrink more by utilizing knowing that those don't care exist. So that's a very interesting paper that did really some non-trivial uses of the covering arrays. And then this brings us to the locating aspects of the problem. And I'm running a little bit of time, but this is the definition of detecting and locating arrays that Charlie mentioned today. So now you want to use the array to not only detect that, to find out that this row contains some interaction, but you want to know which interaction caused the problem. So you need much more escaping redundancy, like in error correction code or in combinatorial group testing, to be able to detect which interactions cause the errors. So this is a paper that Coburn and McClary introduced these concepts. Also the relations with combinatorial group testing. And I, some co-authors, Brett is here as well, we looked at, there is a certain restriction on the existence of this detecting array, which is my D has to be smaller than the alphabet. Because there are some specific combination of errors, all of which are using the same, all the values in a certain factor, that would not be locatable. There exists no array for it. So what we did is we looked at locating arrays, allocating array specific to a neural graph, which on itself is not so useful, but it could be useful in another context. I was just going to give you an example here. If I know my error graph is this, okay, value 0 in factor 1, value 1 in factor 2, and represented by a K-per-type graph, this is a locating array for that graph. So for specific graphs, I can have locating arrays. Of course, this is what I want to discover, so I won't be able to set up this in order to discover the errors. But this is useful to then look at what I call error locating arrays, which is a generalization of the detecting arrays, in which you tell me a class of graphs. What's the class of graphs you're interested in? These arrays work for this class of graphs. So the detecting arrays is the class of graphs in which the number of edges is exactly D. So you focus in saying, okay, I know the number of errors, number of edges is D. So then this array works for everyone in this class. But I could decide looking at different classes. In particular, if I say that my graph is locatable, which is one that doesn't show the bad configurations that make my graph not being located, right? There is a definition in that paper about what locatable means. Then I could have more arrays. That, as long as the graph is locatable, I am able to create the error locating arrays for them. And actually, covering arrays help. So if my graph is locatable with these parameters, number of edges, strength, and K, I could use an orthogonal array of enough strength to build it. If, moreover, not only locatable, but I know that it's safe values, that exist one value for each factor not involved in any edge, if I know who the safe values are, then I can have a covering array with smaller strength that is indeed an error locating array for that kind graph. So there is interesting things like this. Finally, I would like to point out, this is known for 10 years, but I don't think it has been emphasized. If you have a particular error graph, which could be the forbidden configurations that you know are not possible to be tested, there is a direct relation between an ELA, error location array for this, and a CAFE, which is a covering array with this forbidden configuration. The problems are very related, and I think more could be explored into that relation in the future. An ELA for that age, the best ELA for that age, if I remove one row that distinguishes any of the edges that must exist in that ELA, each row must be able to locate one edge. Remove that, what is left is a CAFE for that graph, which is a covering array that avoids those forbidden edges. So in some cases, like in the cases of the existence of safe values, we can handle forbidden interactions in covering arrays just by studying this error locating arrays a little bit more. And I'd like to thank you.
We have time for one quick question, if any. Okay, if not, let's thank Lucia again. I'm sure she'll be happy to answer questions.